and I'll be talking about linear independence, alternance, and applications. This is joint work with Shubhangi Saraf and Ilya Volkovich. So the main objects that we'll study in this talk are arithmetic circuits. These are models that compute polynomials via addition and multiplication gates, and these gates naturally just take their children's and outputs the operation on them. So one of the central problem in the field of arithmetic circuits is the problem of polynomial identity testing. Here you're given a circuit C and you have to test if it computes the identically zero polynomial. So here given means that the circuit is given to you in a white box manner that you can see the circuit, or in a black box manner where all you're allowed is to evaluate your circuit at a point of your choosing. Note that there are randomized algorithms for this problem thanks to the Schwartz-Zippel lemma, but de-randomizing PIT is one of the central problems in algebraic complexity. The focus of this talk would be on black box PIT. Note that this is stronger than the white box PIT question. So one of the seminal work in black box PIT was this work of Agarwal, Saha, Saxena, Saptarishi titled Jacobian Hitch Circuits. Here, ASSS used the notion of algebraic independence to give a unified approach for doing PIT for various interesting circuit classes. So there were various different interesting techniques floating around for a bunch of PIT models. Seems a bit ad hoc, but ASSS came and used the notion of algebraic independence and gave a unified approach to doing PIT for a bunch of special models. So before elaborating a bit on their result, let's study what does it mean by algebraic dependence and algebraic independence of a bunch of polynomials. So if I have n polynomials, I will call them that they are algebraically dependent if there exists a non-zero polynomial h such that h composed with fi's gives me the zero polynomial. In some sense, h, when you compose with the f variable, annihilates them. And naturally, we'll just define algebraic rank of a set of polynomials to be the size of largest algebraically independent subset. So one could ask is, how would I use this algebraic independence notion to do PIT? So here's the main connection. So if we could construct a homomorphism, so if we have a map phi that maps n variable polynomial ring to k variate polynomial ring such that it preserves the algebraic dependent structures among fi. That is, it maps algebraically independent polynomials to algebraically independent polynomial. Then, if you compose any non-zero polynomial or for any polynomial c on fi's, and that is non-zero, this is if and only if c composed with the image of fi's under the map phi is non-zero. Further, if your map has this property that it takes n variables, which is a growing parameter, and map it to k variables, which is bounded, this would be very helpful for us because we have made a n variate PIT instance to a k variate PIT instance, which is much more manageable. So just demonstrating that in a circuit format, that is, suppose you have a hard looking circuit in front of you, and you could find some chunks at the bottom which are manageable complexity. So you could find F1 up to Fm at the bottom of the circuit, and on top is a notorious looking circuit, but you have a map phi such that it preserves the algebraic independent structures of these fi's. Then if you just replace this f by phi of fi, that is, once you apply this homomorphism on this circuit, you can just do PIT on the image instead of doing the PIT on the original circuit. So that was the first idea, that if you can have these nice maps, then you can do PIT. The other is that if your field is of characteristic 0 or large, then Jacobian, an operator I'll define shortly, captures the algebraic independence. So let me elaborate on that. So Jacobian is this operator that is a matrix where entries are the first order partial derivatives of my polynomial fi's. And there's this following theorem by Jacobi, which says that if your characteristic is 0 or large enough, then algebraic rank of these polynomials, which is a seemingly notorious object, is equivalent to rank of this Jacobian matrix, which is something much more easier to understand. So this is what Jacobian criteria gives us. It helps us manage algebraic rank in terms of just rank of a matrix. And so ASSS combined this idea of Jacobian and the faithful homomorphisms idea. So ASSS used this approach along with Jacobians to construct hitting sets for depth 3 constant upfront circuit and constant occur constant depth circuits over fields of characteristic 0 or large enough. So one could naturally ask this question, what if the characteristic of the field is small? Note that here the Jacobian criteria just fails. For instance, if you have these two polynomials, x to the p minus 1y and y to the p minus 1x, they are algebraically independent. That is, algebraic rank is 2. But if you look at the Jacobian, that's just rank 1. So there have been some work in trying to extend the Jacobian criteria over fields of characteristic small. For instance, the work of Pandey Saxena Sinha Babu and later Chatterjee and Saptarishi studied the algebraic independence problem, Jacobian and its applications in special settings, but these are very, very restricted settings and the problem is largely open. So one could ask this question, if my motivation is just to do PIT for special circuits, can I just work with linear independence instead of algebraic independence? So here's the key idea behind it. That is, if I have a sum of TIs, so I have a circuit which looks like summation of TI, where TIs are easy polynomials, that is, they have manageable complexity. So if we assume that this is the optimal way to write it, that is k is the smallest way to write this thing, then we can assume that T1 to Tk are linearly independent. Why is that? Because if they were linearly dependent, I could just use that linear relation to reduce the top fan-in. So we get the linear independent structure for free. Now, there are two main questions, like, is there a way I can project from n variables to k-ish variables such that I ensure my linearly independent polynomials stay linearly independent? This is analogous to the homomorphism map phi I discussed earlier, which reduced n variable to k variables, keeping some structures alive. And also, is there a tool like Jacobian that helped me study linear independence, just like Alternant did, just like Jacobian did for algebraic independence? So the answer is this folklore object in mathematics called the alternant. So some notation before I delve into it. So I'll refer to capital X, Y, Z as a set of variables and small lowercase xi as just one variable. And when I refer to capital X1, capital X2 up to capital Xm, here I mean independent copies of my variable set X. So alternate of a set of polynomials is just, you look at independent evaluations of my polynomial. So I'll write my F1, I'll evaluate at k disjoint copies, similarly F2, F2, F3 up to Fk. This should be k. So here's a lemma. If my F1 to Fm in the polynomial ring are linearly independent over the base field, this is equivalent if the determinant of this alternate matrix is a non-zero polynomial. And this works over all field. And this is a very easy exercise. So nothing crazy going on. The folklore object. But note that this directly is not helpful for us for PIT applications, because if you have polynomials of some complexity and you apply determinant on top of that, you're making your model even more complicated. So we need something more. So here's that other bit. We call this small witness for linear independence lemma, and it's a very important technical contribution of this work, but very simple and natural. So what it says that if you have a field F and you have k polynomials in the field such that they are linearly independent over the base field, then there is a set S of size k minus 1 such that if you think of those polynomials as in terms of just these S variables, that is, you think of all the other variable in the base field, then over that bigger field, they continue to remain linearly independent. So let me just elaborate what I mean by linear independence over the big field. So usually we look at summation alpha I fi non-zero, where alpha is just in the field. But since here this field is fx, not an s, so all the variables apart from s, even if you allow for these complicated alpha i's, this linear combination will still be non-zero. So, but if you want to get a line out of this lemma, it would be that we can just work with k minus 1 witness variables. That if you can just keep them alive and put them everything else in the base field, my polynomial will continue to remain linearly independent. So now let me combine this lemma along with the alternate criteria. So think of my polynomial in fx, and I'll look at a partition of the set of variable x into y and z, where y is the witness variables and z is everything else. So I'll define alternate of f bar with respect to these y variables, where I'll just take independent copies of the y variables. That is, I don't touch the z variables, and I just take independent copies of the y variables. And if we just look at the SWLI lemma and the alternate criteria, it gives us a following corollary. So it says, if f1 to fk are fz linearly independent, then this is equivalent to saying that determinant of this matrix is non-zero as a polynomial. So now we have a operator which might be more amenable for our applications in PIT. But before going into that, I'll just give a proof for this small witness for linear independence lemma, because the proof is using induction and it's very crisp. So let me just write a reformulation of it. That is, if you have k polynomials in a polynomial ring fx, such that they are f linearly independent and the number of variables is greater than k, then you can always find a variable xi in a variable set such that you can adjoin that variable to the base field and your polynomials will continue to remain linearly independent. And you can keep on applying this to get the lemma as how it was stated before. So the proof is by induction on k. So I'll use the induction hypothesis on k minus 1. So I have f1 to fk minus 1, and they are f linearly independent. So we have then the condition already hold, the size of x is greater than or equal to k minus 1. So I get a variable xi such that these polynomials are fxi linearly independent. Let me call this fxi as a new field k. So k is fxi, should be fxi. Now I'll apply this again. Note that the polynomial f1 to fq minus 1 are also k linearly independent. That's what I concluded here. And note that the number of variables, that is size of x minus 1, is still greater than or equal to k minus 1. So I'll get another variable xj, which is not xi, such that f of x1 to fk minus 1 is also k xj linearly independent. So this is equivalent to saying that we get f1 to fk minus 1 is fxi fxj linearly independent. So, wow, I see. Now suppose that f1 to fk is linearly dependent for both fxi and fxj. If that's the case, we get some linear dependencies in xi's and some linear dependencies in xj. And if you subtract both of them, you get that 0 is equal to summation t equal to 1 to k minus 1 utxi minus vtxj ft. But note that we prove that my polynomials f1 to fk minus 1 are fxi fxj linearly independent. So all these expressions have to be 0, which imply that utxi is equal to vtxj for all t in k minus 1. Well, these are polynomials on disjoint set of variables. So these expressions, both of them have to lie in the base field. So this gives us that f1 to fk minus 1 are f linearly independent. But that's a contradiction because we assume that the polynomial are f linearly independent to begin with. So that's a contradiction which concludes the proof of our lemma. As I said, it's a very simple and crisp proof. Now moving on to applications. So before that, I have to define the model for which we do PIT. So let me define depth for Akar-K formulas. A depth for Akar-K formula is sum of product of Pij, where Pij are some S sparse polynomial. And This formula is occur k if each variable occur in at most k many Pijs. So that's the notion of constant occur formulas. And this might feel artificial, but this is a much stronger assumption than what we use usually, like multilinearity assumption, multi-k assumption. So this is a much general class than all those restrictions. So but there are some tricks that we know that we can apply on this model. For example, we can always bound the top fanon of this model for our applications in PIT. That is, suppose we pick any xi in the variable set of f, and if we look at fx minus fxi restricted to xi equal to 0. Note that this is not equal to 0 because xi is in the variable set. And if you look at this expression, suppose the top fanon was originally t, and if you look at fx minus fx restriction to xi equal to 0, the top fanon here would be at most 2k, because everything which does not depend on this k variables or on this k occurrence of xi will just cancel. So, okay, we can bound the top fanon. So we'll just assume that our depth for constant occur circuit is given to us in a top fanon restricted setting. And as we discussed before, we can always assume that in these kinds of representation, the product gates are linearly independent. So we'll just assume that TIs, which is products of Pijs, are linearly independent. So now we'll apply our small witness for linear independence lemma. So we'll find a set Y inside of the variable set such that it witnesses the TI's linear independence, which means that alternate with respect to the Y variables, which is this, has non-zero determinant. But we want to find a setting of the Z variables such that we'll be able to hit this polynomial. So it's a non-zero polynomial, but we want to hit it. So let's just look at one particular term here. So look at one particular product expression. So a TI is product of some sparse polynomial. Let's break those sparse polynomials further. So I'll break it into two parts. The first part is the part which does depend on my witness variable Y, and other is the part which does not depend on the witness variable Y. So note that, let me just call this one Ti prime and this one Ti double prime. Note that Ti prime is a product of at most k square many Pijs. Why is that? I have roughly k witness variables and each witness variable has occur k. So I get roughly k square many Pijs here. So the sparsity of this product Ti prime is at most s to the k square sparse. Right? And note that Ti double prime is just independent of I. And now if you look at the alternate expression here, you'll realize that this Ti double primes are just scaling. So you can take them out. So this determinant expression simplifies and you'll get some product of Ti double primes, which is just product of sparse polynomial because Ti double prime was a product of sparse polynomial, and determinant of Ti primes. And as we discussed that sparsity of each of these terms was roughly s to the k square, and the k cross k determinant on top of it will just blow the sparsity of this expression in terms of k. So at the end, what you get is just equivalent to a product of sparse polynomial, which is something we know black box PIT for. So if we use an instance of Z variables such that this is non-zero, that instance will keep a linearly independent polynomial independent and thus non-zero. That is, so if we find instead of Z variable alpha bar such that this determinant is non-zero, we'll get that the restriction of Ti's to Z equal to alpha bar will be F linearly independent, which will imply that for that evaluations, my summation Ti will be non-zero. So what theorem we get out of this is that if your K is small, let's say it's fixed right now, then we can give a deterministic poly-S time algorithm for doing black box PIT for size S, occur K, depth 4 formulas, and this works over all field. And in general, instead of working with occur K depth 4 circuit, we can define occur K sigma pi curly C formulas, where curly C is a circuit class of your choice. So you can think of it as formulas, ROABPs, constant depth circuits. You can choose it. So, but the occur K restriction gives you that if your F is some subproduct ofCij's, where each Cij belongs to that circuit class curly C, each variable occurs in at most K ofCij's. And for this model, sum subproduct of curly C occur K, we have the following theorem that if your black box PIT of constant y product times constant line summation of for that circuit class, that implies black box PIT for occur K sigma pi curly C formulas. And this is without any restriction on top fans. So if you can get some restricted, so if you can allow constantly many addition and constantly many multiplication on a circuit class, then I can get black box PIT for occur K of that class. And using this, we can cook up some circuit classes where we can get black box PIT, which was not known before, even using ASSS. So let me compare it with the work of ASSS. The main point here is this work doesn't need the large characteristic assumption, but we do lose something. So in ASSS, they define the following notion of occur K depth for circuit. That is, the following circuits, sum over I, product over J, Pij to the EI for arbitrary EI is still occur K for them because powering of a polynomial does not change its algebraic independent structure. That is, if some polynomials f1, f2 square, f3 to the some arbitrary r is algebraically independent, that is equivalent to saying those polynomials are algebraically independent without those powers. So powering doesn't change the algebraic independent structure, but it clearly changes the linear independent structure. For instance, x and x square are linearly independent. Now, we do, and using this, they could take care of this arbitrary power EIs, and they could also do something they call delta depth occur K circuit. We can't do that. We need some kind of a restriction on our addition gates. But we do gain something, as I mentioned previously, that we can cook up some circuit classes for this special C, which they can't solve, because for instance, if you look at depth 3 constant of Fanon as your circuit C curly C here, they can't do, because Jacobian, which is first order partials of this circuit classes, will become complicated, whereas our alternate is just independent evaluation, which stays more manageable. So I'll move to the other application of our techniques. That's in circuit reconstruction. So in circuit reconstruction problem, we are given black box access to your polynomial f, where it belongs to some circuit class cursive C, and your aim is to learn a circuit computing f. So instead of talking about a particular result, I'll talk about a meta theorem which does occur in average case learning kind of scenarios. So here's a kind of result, that is, if you can write your polynomial as sums of products of variable disjoint polynomials in, let's say, 3 such variable partition, such that these Pi's and Ri and Qis are linearly independent. So if you can write your polynomial like this, where Pi and Qis are linearly independent, then you can reconstruct f. That's not a formal linking statement, but I just want to impart a flavor. So if you could write a polynomial like this, and if you have some linear independence condition, then you can reconstruct f. For instance, the famous Yandex tensor decomposition algorithm can be realized like this. So one could ask this question is, what if I don't have this linear independence condition? So these conditions do hold over average case, but if you want to do worst case learning, you can't assume all of this. So what if these conditions don't tend to hold? So let me fix a model that I want to study for a circuit. This is set multilinear depth 3 circuit. It looks like sums of products of Lij, where this Lij is over this joint set of variables. And let me call this each product term as Ti. And if you want to learn this, as I discussed before, we want to find a set of polynomial PIs which divide QIs and PIs which divide TIs and QIs which divide TI again, such that they are linearly independent in the worst case. So a small witness for linear independence lemma comes to rescue here. For instance, for the same reasons again, by optimality of the top fan, we can assume that Ti is optimal, and so these polynomials Ti's are linearly independent. So I can again break my Ti's into part which depends on Y and which does not depend on the witness variables. And note that the things that depend on Y, as I discussed before, are linearly independent because of the small witness for linear independence lemma. Now let R be the rank of whatever that remains. So Ti tilde, let R be its rank. So we can apply small witness for linear independence lemma again on this, and we can further break Ti tildes into Qiz and Rix, where my Qi's would be linearly independent, Q1, Q2 up to Qr. And if you use that, you can write F in the following way, where now my top n, instead of being K, has now been reduced to R, which is something smaller. But we do get this linear independence condition, which we wanted to have in the first place. So we lost some information in the top fan, and our circuit becomes slightly more complicated, but very manageable, and we were able to get this linear independence condition. So using these techniques, what we were able to prove is the following theorem. That is, if your polynomial is n variable degree less than equal to d, and is computed by a set multilinear, the class I described before, there are three circuits of top fan and K of an unknown partition. That is, you don't know what the circuit partition is, then using the techniques I described previously, we can make an randomized algorithm that proper learns F in time poly d to the K to the order 1, K to the K to the K to the order 1, and n. This might look ugly, but that's how these algorithms usually look in reconstruction literature. And this is good because the previous algorithms worked only when the variable partition was known. And in general, if I give you a polynomial and you have to find its partition, that is an NP-hard problem. So we were able to deal with that problem in this special case. So to conclude, we saw a small witness for linear independence lemma, kind of a main technical contribution. We saw alternants, a folklore object in mathematics, being used here for PIT and reconstruction. So the main open question I want to ask everyone is, whenever, especially in TCS, whenever we talk about linear independence testing of a bunch of polynomials, the first thing that comes to mind to people's mind is the Wronskian operator, which is again a very notorious operator. It's not very easy to understand, as opposed to alternate, which is very simple. So the open-ended question I like to ask everyone is, can we see more applications of alternate to places where, let's say, Wronskian gave some results? So that's all. Thank you.